All right, so we're going to switch gears here and move on with our Chapter 3 discussion of alkanes. Up until this point, we focused pretty heavily on nomenclature of alkanes, which is really a way of introducing y'all to nomenclature rules in organic chemistry. All right, now we're going to talk a little bit more about this functional group itself by talking about the physical properties of alkanes. All right, so first of all, let's make sure that we're all talking about the same thing here. An alkane as a functional group means that that molecule contains only carbons and hydrogens and all single bonds. All right, so an example would be pentane here. All carbons and hydrogens, all single bonds. All right, so the first physical property of these alkanes that we're going to discuss is their polarity. What do we think about this functional group? Polar, nonpolar, somewhere in the middle. Nonpolar, and is it very nonpolar or just a little bit nonpolar? Yeah, this is as nonpolar of a molecule as you could possibly have, right? There's only carbons and hydrogens. There's no polar functional groups on there at all. So these alkanes are very nonpolar. They only have these dispersion forces when they interact with their neighboring molecules. All right, so we saw that when we did our solubility tests in the lab, right? Hexane was our example of the most nonpolar solvent that we were going to use, right? So they sit at that very far end of our polarity spectrum. So then this also relates to the next physical property that we're going to discuss, the boiling points of alkanes. Since they have very weak intermolecular interactions with each other, does that mean they have a high boiling point or a low boiling point? Low boiling point, right? In fact, because they have those very weak interactions, as far as molecules go, they have very low boiling points. All right. In fact, alkanes with fewer than or equal to 4 carbons, let's say number of carbons less than or equal to 4, these are actually gases at room temperature. So if it's a gas at room temperature, what does that mean about its boiling point? It means that its boiling point is lower than room temperature, right? So very, very low boiling point. If we increase and we're between 4 and 18 carbons, these are liquids at room temperature. And if we have more than 18 carbons, these are solids at room temperature. And 18 carbons is a crap ton, right? So most of our alkanes are either gases if they're on the smaller end or liquids if they're on the larger end. All right? Well, now what we can see just from this here is we said that they have very low boiling points, but we do see this trend here where our boiling point increases as our number of carbons increases. Okay, so methane with just one carbon has the lowest boiling point, ethane with two a little bit higher, et cetera, et cetera, et cetera. So as we increase the number of carbons, our boiling point of our alkane increases. So why is that? Okay, so remember that dispersion forces is an intermolecular interaction that happens just by virtue of molecules having surface area that comes into contact with other molecules. So the more surface area a molecule has, the stronger its dispersion forces. So larger molecules always have stronger dispersion forces than smaller molecules do, just because they're bigger and they have more surface area associated with them. So why? Because our dispersion forces, they increase with increasing surface area. And larger molecules have more surface area. All right, so the larger our alkane is, the higher its boiling point is going to be, and that's because these dispersion forces increase with increasing surface area, right? So larger molecules have more surface area. All right, another sort of consequence of that is if you have an alkane that have the same number of carbons, but one's a straight chain and one has branch points in it, the straight chain alkane will also have a higher boiling point than the branched alkane. And that's also because of surface area. All right, so we're also going to note that our straight chain alkanes have a higher boiling point than branched alkanes, with the caveat with the same number of carbons. Okay, and again, why is that? Again, simply more surface area. Okay, so that means that pentane compared to 2-methylbutane, since these have the same number of carbons, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, right? This one would have the higher boiling point. This one would have the lower boiling point. Not by much, they're pretty close, right? But nonetheless, that is a consistent trend that we see. More branch points you have, the lower the boiling point for that number of carbons. Okay. So polarity, boiling points, and the last physical property we're going to discuss is how they look and smell, their appearance and odor. All right, so they're either a colorless gas if they're one of the small ones, or a clear liquid if they're one of those medium-sized ones. And those really long ones form these white, waxy solids. All right, and that term waxy meaning like not like a crystal like we saw with our caffeine where it formed those kind of crystal structures. Instead, you basically just get like this gross little paste for those longer chain alkanes. It is a solid, but it's more like a waxy sort of substance than it is a crystalline substance. So not crystal. All right, and these alkanes, they have a gasoline-like smell. Or really, they might take offense to that. Gasoline smells like alkanes. That's because gasoline is made of alkanes. Gasoline is a mixture of alkanes that have a varying chain length to them. High octane gas, right? What does that have more of? That 8-carbon alkane, octane. Okay, so yes, gasoline is going to be kind of the smell of those compounds. All right, now we're going to move on and we're going to talk about reactions of alkanes. And in just about every other chapter that we encounter, this reactions discussion takes up the bulk of our lecture, right? We spend most of the time talking about reactions of functional groups. Alkanes are an exception because they're super boring. They do not have any functional groups. They're highly unreactive molecules, with the exception of one big one here. Speaking of gasoline, combustion reactions. All right, so our alkanes will react with, what's our other reactant in a combustion reaction? Oxygen gas. And we always produce the same two products in a combustion reaction. Carbon dioxide and water vapor. So you can't do much with alkanes other than blow them up. All right. These reactions are important. I mean, this combustion reaction is probably the most widely performed reaction on Earth right now because it releases a crap ton of energy that we've harnessed to power the world, right? To power our lights and everything like that. Your car uses it to go down the road. So these reactions here, we're going to note that they release a ton of energy. All right, they're also why we got a little bit of a carbon dioxide problem on our hands at this point in human history. Okay, so what we're really going to take this opportunity for alkanes to do is, again, mostly when we introduce a functional group, we talk about chemical reactions of that functional group. But we're not going to do that here because there's not really any interesting chemical reactions that occur other than you blow it up and you create two inorganic molecules, right? So we're not doing much organic chemistry with a combustion reaction. Instead, we're going to use this as an opportunity to kind of talk about the shapes of molecules, right? One of the things that we got to remember to do in organic chemistry is we're always drawing stuff in 2 dimensions on the page. It's almost more like a drawing exercise, and we forget that what we're talking about are these 3-dimensional molecules, right? And so we want to kind of keep that in mind and make sure to tie together what we see on the page in 2 dimensions and what's actually happening in 3 dimensions with those molecules, all right? So we're going to talk a little bit about the shapes of these molecules, importantly because, let's just kind of note here, let's go back to my example, my pentane. because we're carbons and hydrogens, all single bond by definition, what does that mean about the hybridization of each one of these carbons here? SP, which one? SP3. They are all SP3 hybridized carbons. Which means that they all have what geometry? That tetrahedral geometry. All right, so we're going to introduce a new kind of way of drawing our molecules that captures that geometry a little bit better. All right, what we call dashed and wedged bonds. Okay, so up until now, whenever we've drawn a molecule, we've used these straight bonds here. So for example, let's look at this molecule right here. All right, but as we said, this carbon in the middle right here is sp3 hybridized, which means that it's a tetrahedral. So this drawing right here is really deceiving. It's kind of like taking this molecule and flattening it out into 2 dimensions. All right? This drawing right here does not accurately convey the shape of that molecule. All right, and so I just wanted y'all to convince yourself. So we got a few models that are built that are kind of on the table. I know we're all pretty spread out, but let's kind of pass them around and stuff. So this molecule here I have with 3 carbons. I omitted the hydrogens just for the sake of simplicity here. All right, and what we want to note is that this does not form a little cross that sits flat on the table here. Okay? In fact, if I were to hold it such that all my carbons are in a line here, I have 1 chlorine atom pointed out at you and 1 chlorine atom pointed back at me, right? That's that tetrahedral geometry, and we have a way that we can draw that to more accurately capture the orientation of these bonds. We're going to start with our carbons all in the same plane. All right, so these flat bonds are in the plane of the page. Okay? So plane being right down the middle. And then I'm going to show one of these chlorine atoms is sticking out of the page. And for that, we use what we call a wedged bond. So I'm going to draw this little wedge. With my chlorine atom on it. And the wedge indicates that this bond, so this is a wedge, means that it's pointed out of the page. All right, so I have 1 chlorine atom sticking out at y'all. The other one is pointed into the page, pointed back at me, and that's what we use these dashed bonds for. These are pointed into the page. All right, so this drawing over here on the right more accurately conveys the shape of my tetrahedral carbon, right? Where I have two bonds that I can put flat, but then I have one pointed out at you and one pointed back at me. And so that's what we use our dashed and wedged bonds for. The wedge means that it's pointed out of the page, sticking up. The dashed means that it's pointed into the page. So if I took my molecule and laid it down on its side like this is exactly what I've drawn. With my carbons flat on the page, one chlorine pointed up, one chlorine pointed down. Okay? So we can use these drawings to more accurately represent the shapes of our molecules. Sometimes what we're going to sort of see is sometimes we have to do that. All right? Sometimes we're going to have to use these dashed and wedged bonds to correctly display our molecule. Sometimes we can get away with just our lazy flat bond way of drawing like we did over here. All right? And we'll talk more about when that is, especially next week when we talk about stereochemistry. For right now, you're just kind of trying to wrap your head around this different drawing and how it conveys bonds pointed up and bonds pointed down. Okay? Cool. All right. So the other thing that's important about alkanes to keep in mind is alkanes rotate about their single bonds. Single bonds, and we'll talk about this in a little bit, but as opposed to double and triple bonds, are always rotating about. All right, so we draw butane like this in this little zigzaggy structure, but importantly, it's not just frozen in space in this zigzag here. It's constantly rotating about those single bonds. So I could also draw butane like this. That's the same molecule, right? You can convince yourself that if I were to give you this on a nomenclature quiz, you would name it the same way. That would be butane, right? That 4-carbon chain. So these are indeed the same molecule, just different rotational states. So this thing here, butane, we like to draw it like a zigzag. It's not just like that. In fact, butane's a gas, right? It's one of those 4-carbon alkanes. If this room were to be filled with butane, we'd all be having a bad time, all right? But what this molecule would be doing is twisting about that single bond over and over again as it's rotating through space, right? This is also butane, just a different rotational state of that molecule, all right? So single bonds, molecules are always moving about, right? Always dancing about. One of the ways in which they move is to rotate around their single bonds. Okay. So we're going to discuss this rotation quite a bit more here. We got to graduate to a new way to represent our molecules before we can talk a little bit about rotational states, what are called Newman projections. All right, these Newman projections are a new way to represent chemical structures and we're going to use them to study bond rotations. All right, so step one, we're going to have to learn how to draw them. All right, so given a molecule, how do we draw its Newman projection? Once we get that, then we're going to use them to study our bond rotations. All right, so first of all, our Newman projections kind of all look the same to start out with here. So how do we draw what I'm going to call the shell of our Newman projection? This is what's going to be the same for all your Newman projections, and you're going to kind of decorate it differently depending on your specific molecule. All right, so let's get an example molecule here. Okay, and what we're going to do is we're going to look down a specific bond. All right, so what the heck do I mean by that? I mean, this is my molecule here, and I'm going to look with my eyeball down a specific bond here. Okay, so step one, we're going to draw this little Mercedes symbol kind of thing. All right, trigonal planar shape. Okay, so I'm going to do my Newman projection down here. All right, when we draw that little Mercedes shape, that intersection is our front carbon. All right, so what do I mean by that? Again, I'm taking this molecule and I'm looking at it in this specific way where I'm looking down a bond, right? So I'm looking at this carbon right here. That's represented by the intersection of those line segments. All right, but since I'm looking directly down that carbon, there's another carbon right behind it that I can't see. And we're going to now, to represent that, we're going to draw a circle. That circle is going to represent the back carbon. All right, so with my Newman projection here, I'm going to now draw a circle around the middle. And that circle that I just drew represents that carbon that's hidden behind. All right, so my carbon that I colored in orange here, sort of behind where I'm looking, behind that red carbon, that's what's represented by that circle. Okay, and lastly, we're going to draw the bonds off our back carbon. So one of those bonds is the one that's hidden between these front and back carbons here. And I'm going to draw my other bonds coming off of that back carbon. All right, so in red here, the ones that are connected to that central intersection here. These represent my front carbon bonds. And the ones that don't touch the middle, they only touch the circle here. These represent my back carbon bonds. So this little wheel spokey thing right here, old-timey wagon wheel, is our Newman projection, the shell of our Newman projection. And we're going to fill in each of these bonds with what we see in our molecule, for what our specific molecule is. All right, but this is the same shell that you'll use for all your Newman projections that you draw. All right, so let's take this specific example And we're going to start filling in here. Let me get rid of some of these colors so it's not too confusing. Well, maybe it's fine. Okay, so again, I took my butane and I'm orienting it. So here's my butane when it's all zigzaggy. And now I'm turning it and I'm looking down a specific carbon here. Right, that's the goal of our Newman projection. We got my front carbon here and our back carbon here represented by that circle. So what I'm going to draw is the bond that's pointing up on that front carbon is a methyl group. So I'm going to draw a methyl group pointed up. What are my other two bonds on that front carbon? One's a methyl group. What's the other two? Hydrogens. So my front carbon has a methyl group and two hydrogens. Now I'm going to go to my back carbon. All right. If I'm looking at my back carbon here, I have a methyl group pointed down. So I'm going to draw that methyl group pointed down. And there's also two hydrogens. All right, so I want everybody to grab their molecule of butane and turn it in such a way that we're looking at it with our Newman projection. Right, where I have a methyl group pointed up on that front carbon and two hydrogens pointed down on that front carbon. When I go to my back carbon, which is hard to do, we have our methyl group pointed down and our two hydrogens pointed up. All right, these model kits are super helpful, especially in these next few chapters when we're talking about shapes of molecules. I loved my model kit. It's just very hard to get a sense of how these things are in 3 dimensions by looking at these 2D objects. That's our goal. I mean, we have to draw it on pencil and paper, so we're going to have these different ways of representing these molecules, but you want to be able to connect what that looks like there to the molecule, to our actual shape of our molecule that we built with our model kits. Right, so I started out with my butane in this zigzaggy line here, but I was looking down this bond in particular, so I turn it, and this is what my Newman projection represents. Right, my front carbon with my methyl group pointed up and my two hydrogens pointed down. My back carbon here, which you can't see because it's blocked by that front carbon, but it's got that methyl group pointed down and those two hydrogens pointed up. Right? So that's what I'm representing with my Newman projection. Okay, so now that was normal old butane. Let's take this and decorate it a little bit. Now I'm going to put a fluorine on a wedge on that second carbon. That fluorine is represented in our model kits by an orange bead. And I'm going to take a chlorine, put it on a wedged bond, meaning it's pointed into the page. That chlorine is represented by a green bead in our model kits. And again, I'm going to look down this bond here. All right, so we're going to always draw the shell of our Newman projection the same. We got our little wagon wheel here. Put in our Mercedes symbol. Circle around it. Draw the bonds off that back carbon. And I want everybody to take a second. We're going to pass around our model here that is built for this molecule. All right. If I want to lay it down on its side, like it is on the page, we see our carbons are in the plane of the page. That's why they're the flat bonds. We have our fluorine pointed up, and we have our chlorine pointed down into the page, right? So this is this molecule that we just built with those proper orientations of those two halogens. And you're going to take this and spin it and look down that bond between carbons 2 and 3 to draw in your Newman projection, right? What should you be putting on each one of these bonds here? All right, so take a second with those model kits. All right, our goal is to translate our bond line structure into a Newman projection. Pass those models around. I want everybody to play with these model kits, all right? Everybody's not too cool for the model kits. Just take a look at them. I swear it'll make it make more sense, all right? Fatima, you want to take a look at this one? Okay, so since I'm looking down these two carbons here, again, just to kind of label again, this is my front carbon. So these are the bonds coming off of that front carbon. This is my back carbon. Oops. Represented by the circle in my Newman projection. So these are the bonds coming off of that back carbon. On that front carbon, I have my methyl group up here, so that's pointed up. I have my fluorine pointed out of the page. So if I take this molecule and turn it so that I'm looking at it this way, does that mean my fluorine's pointed on the left or the right? Whoop, wrong way, left or the right? So my fluorine's over here on the right-hand side. All right, can I see that real quick? All right, if I'm looking down this bond here, my fluorine is pointed on the right-hand side. It was pointed out of the page when I laid it on its side. When I flip it over and look down this bond here, my fluorine is pointed out to the right. That means that my hydrogen, that implied hydrogen, is over here on the left. If I look at my back carbon, that methyl group is pointed down. My chlorine, which is pointed into the page here, would then be on the opposite side of where my fluorine is, right? My chlorine over here is pointed to the left. All right, and my hydrogen is on the opposite side. Okay? So we're going to take our molecule here with its dashed and wedged bonds. The wedged bond means it's pointed out of the page, so when we turn that, That means it's going to be over here on the left-hand side. Nope, on the right-hand side. And our chlorine is pointed in the page, so again, when we turn it and look down that specific bond, that means it's over here on the left-hand side. All right, make sure that you can see how we got this Newman projection using these model kits here. All right, don't be shy about taking it and spinning it around until it makes sense. Okay, so we said that this was a way of representing molecules here. We're going to use Newman projections a few times throughout the course. For this particular chapter for alkanes, we're going to use them to discuss what we call rotational conformations. All right, so this is what we're going when we're going to tie together what we discussed about Newman projections with what we discussed about these molecules rotating about their single bonds. And we're going to start with our regular old butane and its regular Newman projection. All right, so regular old, I mean in our zigzag conformation. Again, we're going to do our Newman projection looking down this bond here. Okay, so again, we have our CH3 pointed up. And the other methyl group in the back pointed down. All right, and just to color code to be clear, this is this carbon here. This one that I'm looking down is the middle of my intersection of those line segments. The back carbon is represented by the circle itself. And the one that's pointed down is off of that back carbon, that other methyl group. Okay, so what we're going to do is we're going to make a big graph here where we're going to take our Newman projection. I'm going to need some space, so I'm going to shrink it on down. Okay, we're going to start with this conformation right here, and what we're going to do is we're going to make a graph of energy, and then what we're going to do with our y-axis here, our x-axis rather, is we're going to rotate that single bond. All right, so we're starting out in our staggered conformation here. All right, this is what we call, with the two methyl groups on opposite sides, this is what we call our staggered conformation. All right, so what we're going to do is we're going to take this here and we're always going to keep our front carbon, whoops, that didn't work out. We're always going to keep our front carbon the exact same. So I'm going to draw another Newman projection with that front carbon in the exact same place, right? We're not going to change that front carbon. But again, we're rotating about that single bond. So what we're going to do is we're going to start rotating that back carbon. Okay? So we start out here. When we're rotating, we first get to this point, our bonds are originally staggered, right? And then as we start to rotate, we reach this state where our bonds are now all parallel with one another. The bonds in the front carbon are parallel to the bonds on the back carbon, right? When I start rotating, start from staggered, and I start rotating, I get to this point where these two bonds are now parallel with one another. The bonds on the front carbon are parallel with the bonds on our back carbon. So when I'm drawing this in here, now instead of drawing my bonds off in space, like, equally spaced over there, I'm going to draw them parallel to the bonds on my front carbon. Okay? Since I was taking this methyl group and rotating it this way here, that means if I'm going to fill this in, I have my methyl group over here, my hydrogen, and my hydrogen. All right, let's color code to keep track of these two methyl groups. All right, so when my bonds are equally spaced, we call that a staggered conformation. When they're parallel to one another, we call this an eclipsed conformation. All right, and what we want to do is think about what happens to the energy as we rotate about that single bond. All right, there's kind of this simple principle in chemistry, which is atoms don't really like each other. They like to be as far apart as possible from one another. So when everything's all nice and staggered, all of my atoms are all equally spaced out. When I've rotated it into that eclipsed conformation, now all of a sudden these groups of atoms are much closer together. So by rotating it from staggered to eclipsed, I've increased the energy of that molecule. All right, so now we're going to keep going. We're again going to rotate that back carbon. All right, I'm eclipsed. If I keep going, now all of a sudden I'm back to a staggered state here. Okay. But this isn't the same as my other staggered state, because if I look now, my two methyl groups are much closer together than they were before, right? Now my methyl group on that back carbon has moved up here. Okay. This has a fancy name. This is what we call the gauche conformation. This is staggered, so it's lower energy than our eclipsed conformation, but it's not quite as low as our original staggered. So we're going to hit a minimum here. But notice that we're at a higher energy over here than we started out originally. And now we're going to keep going. We're going to keep rotating. Which means that now I'm going to get to another eclipsed conformation. All right, boom. But now what group is going to be on, what am I going to put up here? I've taken that methyl group and now I've rotated it such that it's eclipsed with my other methyl group. So here's my other CH3. And now not only are we in this eclipsed state here, but we're in an eclipsed state where the two biggest groups in the molecule are directly next to each other, right? So this is what we're going to call our eclipsed methyl state. What do we think about that compared to our other eclipsed state? Is it going to be higher or lower energy? It's going to be higher because, again, those big groups do not want to be next to one another. All right, so again, we're going to start raising in energy here, but now we're going to plateau even higher than where we were before. I did not manage my space very well. All right, if we keep going, I want everybody to take a second and try to draw me what the next state will be if we keep on rotating about that back carbon. All right, notice what's happening to my back carbon, my red methyl group here. As I'm rotating, it's going around and around and around that molecule. So now it's going to be over on this position here. Okay, what would we call this state? Is it staggered, eclipsed, or gauche? Yeah, so I got those two methyl groups next to each other in that staggered conformation. All right, so my energy will have fallen back down to that gauche level, the same as it was before when we had our other gauche structure. All right, if I keep going, I get another eclipsed structure, but with my methyl group over here. Oops. Okay, these eclipsed structures were at these maxima here, but one of them was higher than the other one. All right, so let's say this one will color in orange, and this one will color in green. Where should I go to for this next one, for this next eclipse structure? Up to the orange level or up to the green level? Up to the orange level, because my two methyl groups aren't eclipsed. That's why this one was so high energy. My methyl groups and my hydrogens are eclipsed. But so yes, I'm going to bring it up to that orange energy level. And then if we keep going, finally we're back down to exactly where we started, in that original staggered conformation. All right, so this molecule is constantly rotating about these single bonds, but not all of those rotational states are created equally. We have our staggered conformations that are lower energy than our eclipsed conformations, meaning it'll spend more time in those staggered states than it will in those eclipsed states. All right. And we can also note that the way that we draw it with our zigzaggy line is the most stable of those staggered states, because it's one where our two methyl groups, our two large groups, are as far apart as possible. So our local minima over here, our global minima actually, is that staggered conformation where those two methyl groups are on opposite sides. So that's why we tend to draw alkanes in that kind of zigzaggy line, not because they're frozen in that conformation, but because that is the most stable state of those molecules, right? The most stable rotational conformation. It doesn't mean it's going to live there forever, all right? It does mean that it will spend the most time there. So if we had a room full of butane molecules and we froze time and went in and counted what was in every state, we would see most of them are in this staggered state here with the two methyl groups on opposite sides of one another, right? But again, they're always constantly rotating about that single bond. Cool. All right. So that's what right? So step one was we learned how to draw these Newman projections, these new ways of representing our molecules. And what we used it for was to explore these rotational conformations of butane. We're going to see a few more uses for these Newman projections as we go throughout the course. So again, being able to draw them is really important. I want everybody to take a second. If it was not abundantly clear to you how we got from this bond line structure to this Newman projection here, I want you to take a minute and make sure with those model kits, you can come grab mine if you want, make sure you understand how we got this Newman projection here. All right, it's not witchcraft. It's totally doable, all right? But it does take a little bit of spinning a molecule around in your brain, which is not the easiest thing to get a hold of. All right, cool. We're going to call it there. No, I don't know about when it's running low. I mean, certainly if you go get